In this video, we're going to be talking about stepwise methods for choosing predictor variables in your model. And we're going to do this again in the last video of the playlist as well, where we just kind of get into R and run through an example where I just kind of show off the code and talk about it a little bit more. But this video, we're going to do more big idea overview of what some of these different model selection options are and how they're working differently and why it's usually a good idea to kind of try several of them or all of them in order to find some candidate models. So the reason why we need these systematic approaches that something like R can help us with is because we can quickly get overwhelmed by how many model combinations there really are. So if we have, for example, 8 predictor variables, that's going to quickly add up to 256 model combinations. And rather than me trying to sort through and figure out which ones I want to use and try them and compare them, it would be a lot easier if I just used some kind of systematic method, like the stepwise function in R, to kind of do that for me and to filter out some of the models that probably wouldn't make much sense, and to kind of systematically find what would probably be the most sensible models. Let me go ahead and move myself over here. So we're going to use this example data from the book, which is the seat position data from the fairway package. And so this data is looking at how far away somebody would set their seat from the steering wheel. So we have, I don't remember how many people were in this data set, but we have some number of people, and we recorded this information about them. So their age, their weight, their height when wearing shoes, their height when not wearing shoes. I don't remember what this variable is, to be honest. Their arm length, thigh circumference, I don't know, thigh length, and leg length as different predictors. So hopefully using this information, that helps us kind of understand how far people tend to want to sit from the steering wheel. Maybe that can kind of help us customize different options and understand what car models are best for people with different heights and how to make different car models kind of a good fit for as many people as possible. So let's start with something called backward selection. So backward selection, I feel like the screen is just a little bit off. Sorry, this is going to drive me crazy if I don't fix it now. Is it this one? Yeah, there we go. Okay. So backward selection is we start with a full model. And when I say full model, I mean including all the predictors and terms that we want to consider. So it doesn't mean that we have to use every predictor that exists in a particular data frame that we have. But that we've kind of narrowed down and chosen these are the ones that we want to use, these are the ones that we think might matter, and a full model is going to include all of those. So we start with the full model, and then we systematically eliminate the weakest term one at a time. And when I say term, because it doesn't have to be a predictor as it is, because I could, as we'll talk about later, also include interaction terms as part of my full model as well. So each term, each kind of coefficient has a place in this model. And so what we're going to do is we're going to figure out how the model changes if we eliminate each of these terms next. And then we kind of rank them based on which elimination would make most sense for this model, which would preserve the most predictive power, but has kind of contributes the least to the model among what we have remaining at the moment. And we use a measure like AIC or BIC as kind of our quality criterion, as our standard for choosing that. So in this case, we have AIC. And so as you remember, what AIC does is it figures out which model has the least amount of residual error, but it also adds a penalty for adding more parameters. So if we have a parameter that doesn't really contribute to the model, then it's probably going to add more penalty than it is more reduction in residual error there. And so as we see, we're starting with 283.62 as our AIC, and by removing height, AIC is going down. That means that whatever little residual error is being decreased by including this is overweighed by the fact that it's a penalty for having that term. Um, and as a result, it's better just to go ahead and get rid of it. It doesn't really add anything to our model. Probably what's going on is it's just explaining a little bit of random chance variation, and it probably isn't actually serving as a real predictor if we got to some test data. So yeah, so height would be eliminated next. Then we would have another iteration, and we would see which predictor is next weakest, kind of our next best candidate to get rid of. It may or may not be weight. It may be something else because it's going to shuffle around and change as other predictors go, because other bad predictors are correlated with other predictors. And so when we get rid of this one predictor, it's like, oh, actually, this one's carrying more weight now. So these orders do shift around as predictors go out of the model. Eventually, we'll get to a point where eliminating none of the remaining predictors is actually our best bet, and eliminating any remaining predictors is actually going to start increasing the AIC value. So that's how we know that we've kind of found a best model using this particular approach. One other thing that I'll mention, oops, I don't know why that's still written there. Well, actually, I know why that's still there. One thing I'll also mention is that these AIC values being reported are not the true AIC values, but they're the reduced AIC values. So it's the calculation that comes from this right here, kind of the relevant part, but not the full calculation, including the constant term. So to find this particular value, you would run extract AIC of a particular model, if you're curious about how to find like these values showing up here. Whereas just this AIC of model function is going to find that full value with the constant term added. So again, the constant term is there because it has some nice mathematical properties for making these kinds of calculations. But in terms of just true model comparison, we might as well just use the reduced AIC because that's the only part that's actually changing from model to model. All right. Backward selection is another option where instead of starting with the full model and eliminating terms one at a time, we actually start, oops, I'm sorry, I'm getting ahead of myself. We're still talking about backward selection. So this slide is about AIC versus BIC. So AIC is what we did in the last example. BIC is another information criterion that I could optionally use. As you might remember, BIC is usually just a more selective approach. BIC is going to add a larger penalty to parameters, meaning that it's really only going to select the parameters that are really good, as opposed to anything that is adding any value, which AIC has a pretty low bar for allowing parameters to stay in, versus BIC is going to be a little bit more selective in what actually stays in. And it turns out if we use BIC for the same example, BIC actually chooses a model with only one predictor left, and that is going to be somebody's height when wearing their shoes, which I think is kind of interesting how after going through all this, BIC is just like, a model with just the best predictor is the most sensible model, because again, it's just being more selective and it doesn't like a lot of multicollinearity. All right. One more thing that I'll mention as well here is that even if you enter k equals log of n instead of k equals 2, or leaving it alone, you do get it's showing up as AIC in the output, even though it technically is the BIC value, or I guess the reduced BIC value. So just wanted to mention that in case you feel like there's something wrong. I did something wrong. No, you didn't. This is just what this function does. It still calls it AIC, even though you did it correctly here. Notice also that I did specify direction equals backwards is still the default option, by the way, so if I didn't enter that, it would still do backward selection by default. This, though, will default to k equals 2. So if you want to do BIC, make sure that you do adjust the k argument to log of n, where you set n to be the length of the residuals of your full model. So that way, n is now going to represent the number of observations that you have for the variables that you're choosing. Now, I could have called this n row of the data set as well, and that would probably be fine. But just in case you have some missing values for some of the predictors that you're including, you might rather do this for a safer option because it might end up being a different value because let's say your data frame has 500 observations, but the predictors you're using only have data showing up for 450 of those rows. Then technically it's the 450 that you should be going with and not the 500. So that's why this is probably safer to do as a kind of a standard here. All right, so forward selection is another option besides backward selection. With forward selection, you actually start with an empty model or an intercept model, and you iteratively choose a best predictor one at a time until you get to a point where adding any additional predictors is going to begin hurting your AIC again, or your BIC for that matter. So in this case, we find which predictor is reducing our AIC the most from the intercept model, and then we keep doing iterations until we get to this point where none now shows up as being our best option rather than adding any additional predictors. And in this case, it looks like I think the forward selection and backward selection end up with the same model as before. So I think it's, actually, it's slightly different. So instead of height shoes, it's just height that makes it into this model. So it is a little bit different. I think is leg and age the same there? Yeah, so leg and age are both there. So it does actually end up being a slightly different model in this approach. So it's another candidate that I might consider here. And so one thing that I might do is look at this AIC value and see that's 274.24 and compare that to this AIC value of 274.26. So maybe this one's a little bit better, but I could use some other measures like Luke v. RMSE as another kind of comparison to see which model has a stronger predictive power when looking at non-fitted data for prediction. One thing I will mention about coding forward selection is that it's not quite as simple as what we did over here. You actually now have to define, so when coding, I'll mention this in the coding video, define an intercept model. Basically a model with no predictors added, so it's just going to be like response tilde 1 would be like an intercept model. So LM comma data equals, And then secondly, you have to define what's called a scope model, which is going to be basically the full model that you want the model to consider. So you list all the predictors, all the terms that you want to be considered in this iterative process, and list that out. So we'll see an example here on the next slide. But you want a scope argument here as well. And so over here, it's this is what's called a mixed approach or a stepwise search. And it's really the same setup as what I was talking about before. So you have to define your starting model and intercept model. And then the scope would be listing all of the terms that you'd like to be in consideration. You can say direction equals forward if you want to do forward selection. So maybe I should also add a third step here. Direction equals forward. If you want to do a stepwise search, you would do the same thing, except that you set the direction to be both. And so what's going on here with a stepwise search is that you're actually allowing for adding or taking away predictors in the model so far. So what I mean by that is, and I guess it's not explicitly written out here, is that you have a model and you start with the intercept model. You figure out which predictor you want to add. So you look at your list of predictors, which model decreases AIC or BIC by the most, and you add that in. And then you look at all the additional predictors in the next stage, all the additional predictors that you could add and how that increases or decreases AIC or BIC, as well as the option of taking out a predictor that you've already added in. And so by doing that, you actually go through kind of this another like systematic approach of, oh, well, actually, now that I've added this predictor, now I actually should just drop this other predictor. So it's kind of another way to search and possibly find a better model that you might have missed with just a straightforward or straight backward selection approach. All right, so after doing all this, you might be thinking, oh, so in different situations, I should use different selection methods? The answer is not actually no. Um, all of these methods are valid in really any situation. Really, the only thing that might be contextual is whether you use AIC or BIC, because as I mentioned, AIC usually favors a larger model, BIC usually favors a simpler model. So maybe that is a consideration that you are consciously making about how selective you want to be. But in general, in terms of finding a best model, forward, backward, and stepwise are all totally fine, um, and they're usually recommended as doing all of them to find a best model because you might end up getting different results. You might get the same result every time, but you might actually find some different results and some different candidate models, and then you can kind of evaluate which model seems to be predicting the best. You could use a measure like Luke v. RMSE as kind of another measure to consider. Maybe you're also just thinking contextually and looking at your model candidates and saying which one, maybe I want to favor the simplest model of the three that I got, or maybe I do want to favor the one with the lowest AIC or the one with the lowest Luke v. RMSE. So again, these are all just different ways to kind of search in your data. Now, the book also talks about an exhaustive search, which is a way to kind of look at every possible combination. I'm not going to directly talk about it because I think that it's not always necessary. You can do it. It's a little bit intensive to do it that way. But I think that in terms of like our expectation for the class is that you should at least understand these three methods that we've talked about and understand um, that you can use all of them to find some candidate models and then choose which one you think is the best. And again, it's also possible that you don't choose any of the models that come out of these methods, but maybe they do help you kind of narrow down some ideas. Maybe you still choose a different model for some reason, but hopefully this is a good starting point to finding some candidate models.